Hi, everyone. Thanks so much for coming to our talk. I'm Anna Goldie, and this is Azalia Mirhoseini. We're co-founders of Ricursive Intelligence, and we're doing AI for chip design and chip design for AI, hence the recursive part. Azalia and I, we've been working together since 2016. We met when we started on the same day at Google Brain, and Azalia asked me to be workout buddies. And then we ended up working out together. We ended up working together, and then we started a team together called the Machine Learning for Systems team, where we worked on various AI approaches to different problems across the computer systems and chip design stack. One of those projects was Alpha Chip, but we worked on many other projects there as well, and Azalia is going to go into some more details on that. But our vision in this company is that chips are the fuel for intelligence, and they're basically the silicon substrate for AI. And we need to use AI to design better chips to fuel the next generation of AI models and close this recursive self-improving loop. We started this first step in this direction with our Nature paper called Alpha Chip, which is a deep reinforcement learning agent that could generate superhuman chip layouts in hours instead of weeks or months of human effort. Google deployed this in the last 4 generations of TPU and Axion CPUs, Pixel phones, and Waymo chips. And we think this is kind of a first direction towards closing this recursive loop, because the next generation of Alpha Chip was actually trained on TPUs whose layouts were designed using the previous version of Alpha Chip. But we think this is just a first step. And, we started this company last September to take this to the next level. The Alpha Chip was just one stage of chip design, this layout optimization, but there are many other stages. And we wanted to take all of those on, take on end-to-end chip design, and do so much faster, much better, create chips that are more power efficient and better suited to the AI models that they power. And we see the company in 3 phases. We're currently in phase 1. So in phase 1 of the company, we want to accelerate the chip design process dramatically. It shouldn't take a year or more to design a chip, and it shouldn't involve hundreds or thousands of human experts using outdated tools. And so we want to use new AI methods to accelerate both physical design and design verification. Phase 2 of the company, and the customers we would have in phase 1 would be like the NVIDIAs, the AMDs, the Intels of the world. But in phase 2, if we can quickly design chips, it unlocks the opportunity to do more end-to-end chip design. So given a model, like a new workload, like say the next version of Claude, let's design a computer architecture that serves that model way more efficiently, and then to quickly get to tape out. And so we think that we could help many different frontier labs, especially frontier labs that have new AI architectures that aren't necessarily well served by current hardware, kind of break this deadlock, this hardware lottery. And then in phase 3 of the company, if we have the capability to quickly build chips co-optimized to models, why not build our own chips, train our own models, co-evolve them, and reach this full recursive self-improving loop? And now Azalia is going to tell you a bit more.
So here, we are going to talk a little bit more about the details of what we are doing. So our goal here at Ricursive is to automate the chip design process, everything from architectural design and explorations all the way to GDS2, which is the format that you send to the fabs like TSMC. And what we are showing here on the right side is a traditional flow of chip design. And this is a simplified view. There are many, many phases to chip design. And each of these stages require expensive tools and teams of human experts in the loop. So as you can imagine, all of these kind of complexities and kind of reliance on these very slow tools, humans, makes this process really, really slow. As a result, it takes multiple years to design a brand new chip from scratch. What we are doing here is taking a new approach designing algorithms that scale with compute. So our philosophy here is to have this dual loop optimization, where in the inner loop, we have these our proprietary algorithms that I'm going to show you some examples of them, that they can run 100 to 1,000x faster than traditional tools. And these are going to be used by our outer loop, which is a language model that now has access to this much more faster ways of like assessing and optimizing the flow. So doing this, we are unblocking the AI, the LLM on the outside, to do this co-design and exploration, not just within one stage of chip design, but across the full stack. And what happens here is that then we can throw in more compute into the process, have more accelerators running, and the chip design process gets faster. And due to the co-design process that we can do, that we can make better chips. So that is the unlock that we are excited about. Maybe go to the next slide. So here is a glimpse into some of the tools that we have built in our inner loop. We are showing the timing, static timing analysis engine that we have built. This method runs about 1,000x faster than leading commercial tools, while having a 0.999 plus kind of correlation with the actual tool. Now that we have that, and it's 1,000x faster, this means that we can run this in seconds or sometimes milliseconds, depending on the optimization. And what we can do here is now giving this tool to an AI, our LLMs, that they can optimize around it. Now, in each step, just like any other kind of agentic optimization, they can try different ways of tuning the parameters, different ways of even rewriting our tools in order to get further and further optimization on the target metrics. In this case, we are showing you the wire length metric, which in this case, lower is better. And as you can see, the x-axis here is a notion of compute. Like, we are allowing our AI to use more and more compute and explore further and further. And as a result, it achieves more and more optimization. Now, the way we see the company and what we want to enable is the following. Just like TSMC and other fabs enabled the fabless era, where companies like NVIDIA and Apple could focus on the design process and the chip design process and outsource the fabrication to another fab. We want to unlock the designless era. And what we mean by that is that we want application companies, which are growing every day, powered by AI, to focus on their application side of things. And instead of having teams of hundreds or thousands of chip design experts, they can rely on Ricursive as a platform for chip design. And what we can enable through that is customization of chips to their workloads. And depending on how much the scale at which they serve, even a few percentage of optimization and performance improvement could be a big deal. It could be massively important. But we believe, and this is some of our past work at Google, also showed that we can unlock multiplier performance gain through this customization, heavy customization of the workload and hardware. And that would enable us to get to the true mission of the company, which is recursive self-improvement, where our AIs design their own chips and the chips develop the next generation of AI, and we can co-evolve chips and AI models together and get to the Pareto frontier of cost, capability, efficiency fastest. And another point that we want to, another prediction of how the future is going to look like is that we are going to have a lot more custom chips than we have today. And this is warranted because, again, the scale of which AI algorithms are being deployed. We can have them in robotics application, in automotive self-driving cars, in AR, VR, in space explorations. All of these applications are powered by different shapes and forms of AI. And again, because of their scale, they would benefit from custom chips that truly enable them to be as performant as possible. And in order to enable this like massive growth in custom chips, we really need to transform how chips are designed. And we think AI is the solution, and that's what we are doing at the company. And we have an amazing team. Our team is unique in a way that we have people who have worked on frontier AI like Claude, Gemini, Grok, and so on. And we also have people who have made iPhone chips and worked on TPU chips and like have this deep knowledge of doing state-of-the-art chips. And just having them all together in one place has really enabled us to think about problems in completely new ways. And that's what we are most excited about, having this awesome team. And with that, I think we can.
Happy to take questions.
Yeah, sure.
We can share this one.
Yes. Let's see if there are any questions.
Hi, this was fascinating. Thank you so much. My question had to do with who is the user of recursive intelligence? Is it people who already design chips, or is the idea that people who have no knowledge of chip design would use your product?
I think that's a great question. So in phase one, our customers would be existing chip makers, like the NVIDIAs, AMDs of the world. But in phase two, part of what we're excited about is this democratization of chip design. Suddenly, we could enable companies that never built chips before to use us as a platform to get custom chips.
Thank you.
Hello, thank you for the talk. How many chips have you designed already using your methods?
So right now at Recursive, we are working on advancing the methodology of chips. And so we show our advances with our design partners. But before Recursive, we spent a few years at Google Brain. And our technology, our early glimpse into our technology, where we talked about Alpha Chip, that was used in now 5 generations of Google TPUs, Pixel, Google Pixel, Waymo chips, and Axion CPU chips at Google. And to our knowledge, external companies like MediaTek have adopted it at scale for their own chips as well. So we have a coverage of a variety of chips, from accelerators to embedded devices to data center, general purpose CPUs, and so on. Yeah.
Thanks for the talk. So yeah, you use AI for designing the actual chip, but then when it comes to designing like the DSL, do you use AI to create your own DSL like CUDA or PTX, or?
Sounds good. Actually, we have done a bunch of research at Stanford on doing. I'm also a faculty at Stanford, and I've worked specifically on that, using AI to kind of replace the whole compiler stack. So yes, as you suggested, AI can do that, but that's one solution, and AI is getting extremely good at going from high-level code like PyTorch all the way to PTX, like machine code. That's one aspect, but the other aspect is if we want to design chips that are extremely custom, the programming stack and the software stack becomes a lot easier, because we want to serve one or a few models really well at scale, or some modifications of them. So that makes the job of the software much easier. Even though we want to do it really well, we do it once, and then we serve the model many times.
Thank you.
Yeah.
Good question.
Hello. So I have a question. What are your thoughts on chips customized for models embodied in the hardware? When you talk about customizing chips, are you thinking chips where you can change the software, or because there are upsides of embodying the software in the hardware, right? Yeah, what are your thoughts? I know there are a company like Talas that does this. So, yeah.
I think there's a whole spectrum of like different customizations that you could go all the way from CPU super general purpose GPUs. You can go to like more like an etched, which seems to be optimized for transformer-based models. You can go all the way to Talas. You can burn in the weights. You could go more extreme. You could say, I have some priors on the data distribution of the inputs, and I want to bake that in as well. So we think that by, especially our phase one, by making the chip design process dramatically faster, we can enable this whole spectrum of different bets, different types of computer architectures. But when we say customization, we mean more in terms of like making decisions about the microarchitecture that are very consequential. Like, what are the dimensions of the systolic array? How do you organize the memory hierarchy? And we've, as Azalia mentioned, we found in our work at Google that you can achieve multiplier improvements in performance per total cost of ownership via these types of microarchitectures, whereas downstream, like say physical design, the layout optimization, it takes a very long time, but it doesn't actually impact the performance that much. Maybe you could get a 20% improvement in power consumption at physical design stage, but at architecture, you could get 20x or more. So that's what we mean by customization.